So a student mentioned to me that you guys, apparently Dr. Macedoni mentioned that you don't have to memorize this spectrum, but I would just know that the weak field ones are on the left and the strong field ones are on the right, okay? And so what this is these are all different types of ligands that we can attach to our Lewis acid. And what does something mean if it's a weak field? That's what we're going to go over. So if I have a weak field ligand, is that going to be high spin or low spin? High spin. Who can explain to me what high spin means? What is a high spin pairing energy? Reese?
It means it's going to go up rather than stay on the bottom level.
So yeah, we're going to talk about electrons. Electrons always want to take the path of least resistance. So we're going to talk about how electrons can either be promoted or how they can either pair up with their neighbor as they come in and get attached in these ligand complexes. So strong field. Strong field is going to be low spin. Okay? So, what does a weak field ligand mean? Do you think I'm going to have a high energy gap or a low energy gap? A low energy gap, right? So I'm just going to draw some relative examples here, just so you guys can kind of see relative energy levels. Okay? And so, weak field ligands have high spin pairing energy. High spin pairing energy means those electrons, it's going to take a lot of energy for those going to want to line up, for those going to want to pair up. So they would rather, let me think here. Yeah, these ones will pair up. I'm getting confused now. These ones go up top. Okay. I know this can be really confusing because there's a lot of double negatives. It's like weak and strong and high. Okay. So these electrons, if I put them in, let's say I have 3. Okay. Let's say I have 3 in my Lewis acid. And then I have a ligand that's going to come in and add more electrons to my system. In a high spin system, are these going to want to be promoted or demoted? Promoted. Yeah. These are going to want to rather pair up. I always felt like the taller ones were the ones that...
Well, if it's high spin now,
okay.
It doesn't matter.
I'm thinking of a different example.
Singles.
Okay, I apologize. So high spin, so again, there's 2 different energies here. There's an energy for this to get raised to the next level, or there's an energy for it to pair up with its neighbor, okay? And if it's high spin, it's going to take a lot of energy for those to pair up, for those spins to be opposite, so it's going to want to rather just be on its own. And Dr. Macedoni used the example in class about staying at a hotel with your stinky friend. You know, if he's really stinky, you'd almost rather just walk up 13 stairs. But if it's going to take too much energy to do that, then you'd rather stay with your stinky friend. He kind of just used a little analogy like that in the hotel. Okay, so low spin. What are these going to want to do? These are going to want to stay down, correct. So if they have a low spin pairing energy, that means it's not going to take much energy for those to pair up. So they would rather just be opposite spins of their neighbor. Okay? Okay, how are we doing?
You had a question.
Yeah.
Are high and low spins more a product of the weak and strong field?
Yes.
Okay.
Yeah, so these weak field ligands, they're going to have high spin electrons. Okay? So if we have our Lewis acid and these weak field ligands are coming in, then the electrons in those weak field ligands are going to rather be on their own because they're high spin. So we're comparing the electrons in the system. So strong field ligands are going to have low spin electrons. So when my ligand's coming into my acid, those low spin electrons, they're going to rather just pair up with their neighbor rather than go up to the next level. Because it's going to take so much energy for them to go up here, but since it has a low spin pairing energy, it's just like, okay, well, it's not going to take very much energy for me to pair up, so I'm just going to pair up. Yeah?
RTA was telling us that, another way to look at it is the up spins. You can take the sum of them, the one on the left and the high spin, that'll be
Mm-hmm.
So like that's the way you could like compare like the high versus low.
Yeah. Yeah. There's a lot of different ways you can look about it. The way that I think about it in my head is just the high spin pairing energy. If it has a high spin pairing energy, it's not going to want to pair up. It's going to cost too much energy for it to pair up, so it's going to be on its own. If it's a low spin pairing energy, then it's just totally fine pairing up. Because it's going to take more energy for it to go up high. Okay. We made it through that? I'm sorry, I kind of got confused. Okay, here's an example problem that I want to do. I want you guys to just take a minute of this, and this applies to the principles that we just talked about. So which of these coordination spheres is most likely going to look purple to us?
What's the coordination number on the cobalt?
The coordination number? 6.
Oxidation number.
Oh, the oxidation number? It's not important for this case. You're just looking at the ligands. Can you see these? Yeah, this is CN6. Okay, let's talk about it. Who thinks they know? Chris.
Wouldn't it be the H2O one? Because it's kind of like in between the amount of energy required with bromide and cyanide, which bromide would absorb red light, which would show green, and cyanide would absorb violet, or sorry, that is violet would show yellow. So H2O is kind of like in the middle there, so it would absorb yellow. I'm not sure if it makes sense.
That's correct. Okay?
Good explanation.
Did everyone hear that? Okay? It's going to be, this one is going to be the most likely one to look purple. And the reason Chris explained he knew that is because he looked up there at the color spectrum and said, okay, it's showing violet. So if our coordination sphere is showing violet, then it's absorbing yellow. Okay? And then I look at my different ones right here. Okay? Remember, this is decreasing energy to increasing energy. So on this end, I have a smaller energy gap. On this end, I have a bigger energy gap. So what he did was he said, okay, well, yellow's kind of in the middle, and H2O's in the middle. So that's going to be a relative, it's going to be in between. BR would absorb like in the reds, and what was the other one? CN minus would absorb in the blues and violets. Yeah.
Memorize that, like the relativity of all those.
He said you didn't have to memorize it. I think he'll give this to you, but I would definitely know that this side is going to be weak field and small energy gaps, and that side's going to be strong field and big energy gaps. Yeah.
Where's this switch over from kind of
There's no like real exact point, and I don't think it's that important for this. I think we're mainly just looking at the relative to each other.
So then the weak field strong was dictated by the ligands, like solely?
Yes. Yes, the ligands are either weak field or strong field.
Just to clarify, a strong field like CN would have a low spin because of the high energy gap, so it would have something with higher energy color like violet. Is that how I'm thinking?
Yeah, so if we had a CN of a ligand, I know that that's a strong field ligand, so it's going to have a really big energy gap. So if there's a big energy gap, it's going to take a higher energy light to be absorbed in that gap. Remember, our light has to match our gap perfectly, okay? So if we have a big gap, it needs a high energy light. So you're right, it would absorb like in the violet, blue.
And emit in the opposite.
Emit in the opposite, yep. Okay, we good here? I think I just have one more example problem, then we can just talk about magnetism. So I drew right here, this should look familiar to you, to a smart work problem you guys have. It's an absorbance spectrum, okay? And what I want to know is, this is the ligand you have, and what I want to know is, what color is this most likely? Okay, who can explain it? Michael?
Yeah, so you can do it both ways. You can look at the relativity of the color. Since it's 400 is the wavelength, which is a high energy, you would look at it would be absorbing the violet or blue, so we get the yellow or orange. Or you can look at the actual titanium nitrate, or whatever you call it, nitrite, and then look over on the strong field. It's in a strong field, but not the strongest, so it's like the violet, blue, and then go from there.
Awesome. So what Michael said is there's really two ways you can solve this problem. Number one, I gave you the coordination sphere. So the first thing you can do is just say, okay, I have a nitro here. What's nitro on my relative strength chart? So I come over here, it's pretty strong, so it's going to have a pretty big energy gap. So in that case, it's going to absorb a higher energy light. And that's what our absorption spectrum showed us, is that we have the highest absorbance in the low wavelength areas, which is really high energy. So what you could say is what Michael said, this is going to be absorbing in like the violets and blues, and so it's going to be emitting in the yellows and oranges. Did everyone understand that? Yeah.
Just like it feels like we have to know somewhat like the relative wavelengths of these different colors. So it's like what is purple and what's red? So because then you can kind of go through.
Yeah, your reds are pushing like 600, and violets are down at like 400.
So yellow's like 500, right?
Yeah. Yeah.
So, with the field strength, if, like, looking over here and the graph, so because nitrite has a strong field, that makes it absorb high energy. Okay.
Yep. So if it's strong field, big gap, which means we need a high energy to fill that big gap. Yeah.
High energy always correlates with shorter wavelength.
Higher energy is shorter wavelength. Yep. Any more questions on this before we jump to magnetism?
So what was that?
So this is most likely going to be like yellow or orange. It's going to be, and it's hard to tell exactly just the way the scale that I gave you, but it's absorbing a really high energy light, so it's going to be absorbing violets and blues, so it's going to be like yellow and orange. Okay. And this is something, you guys, I know it's confusing, the crystal field splitting theory. You'll get really more in depth to it in OChem. And so what I think the main important thing to know is relative energy gaps and photons filling those gaps and being absorbed. Okay, so magnetism. What you need to know about magnetism, there's 3 different types, and we're going to go over it. The first type is when all of your magnetic moments are in the same direction. What type of magnetism is this? Ferromagnetism, right? And so if I was going to take a magnet and put it up to this, what's going to happen to my magnetic moments? They're all going to align towards my magnet, okay? And so this is what we think of as like, something that's really going to be attracted to a magnet. I introduce a magnetic field, and all the magnetic moments are going to align with it and be attracted to it. Okay? And these as well, since all of the electrons are going in the same direction, these will also be magnetic by themselves. Okay? So these are going to have a magnetic moment just by themselves, simply because all the electrons are paired in the same direction. Okay, let's talk about our second type of magnetism. What would this be called? Yeah, Reese?
So what was the first one called?
Ferromagnetism. What would this one be called right here, this second one? Paramagnetism, okay? And what you can conceptualize about paramagnetism is there's going to be some unpaired electrons and some paired electrons. So these arrows, these are representing, like if I had a molecular orbital diagram here, these up arrows are saying all my electrons are spin in the same way. Okay? So this one would all be spin. What would this one look like? What would this paramagnetism look like? What would you guys think? These blanks, what are these blanks? These blanks are paired electrons, and these are unpaired electrons. So I'm probably going to have some kind of mixture in this molecular orbital diagram. You know, I'm going to have some paired. Let's say I have all these paired, and then I've got, you know, 2 blanks. There's going to be some paired and some not paired. And what happens when you introduce a magnetic field to this?
Some shift, some don't.
Exactly. Some shift and some don't. And I think the main thing to know is these unpaired electrons will not influence their neighbor. So in ferromagnetism, the unpaired electrons will all influence their neighbors. They'll all go the same way. In paramagnetism, some might go, so you know there's going to be slight attraction there to our magnet, but not all of them are going to be going towards that way, and it's not going to be near as strong as ferromagnetism. Yeah.
Paramagnetism, all the electrons are unpaired.
All are unpaired. Yeah.
Is it only the unpaired ones that shift?
Yep. So that's what we're going to talk about on this next one. So this last one right here, what is this called? Diamagnetism. And what happens in diamagnetism?
Repulsion.
Repulsion, exactly. So if all my electrons are filled, what happens is if I stick a magnet to it, that thing it's actually going to repel a little. Because there's no free electrons, there's no unpaired electrons that can align their moment and come and be attracted to it. So it's going to be repelled. And it's basically as simple as that. It's just knowing the different properties, that these are all unpaired and they influence their neighbor. These are some paired, some unpaired. They don't influence their neighbor. And these are all paired. Ferro, para, and dia. Yeah?
So the example of oxygen would be paramagnetic that we did in class. The example of liquid oxygen.
Yes. Yep. Yeah.
What was the d orbital thing that you drew, like right below it? What were you
Oh, this was just like a molecular orbital diagram, just to say, like, if I gave you this, these are all, I'm just showing you these are all unpaired electrons. And in the way that we show magnetism, these are all unpaired. All unpaireds are going to have some kind of arrow. All pairs will just be blank. I'll stop the video, but I want to do something real quick. Okay.